Okay. So before we discuss intermolecular forces, so let's understand first the kinetic molecular theory. So later on, we will understand why we relate kinetic molecular theory to intermolecular forces. So are they related? Do we need kinetic molecular theory to understand intermolecular forces? So that is our questions. So let's have a recall. Again, participate in the chat box. So just write your answer in the chat box. So this is our question. One is, do gas particles are in constant motion? So yes or no? Okay, so that is correct. So gas particles do not move in constant motion. However, they do move in straight line at first. But when they collide with other molecules, atoms, particles, they collide and will have this random motion. So they'll just collide with each other and then they will move in a different direction. So that is why gas particles are in random motion. So next question. Okay, very good. So let's move to number 2. Thus, the collision of gas molecules is inelastic? So yes or no? Okay, so that is correct. So remember the conservation of energy, that the energy cannot be created nor destroyed. So therefore, that energy is conserved. When it is conserved, that will be elastic. So that is no. And then our last question is, the total energy is conserved in the gas molecule? So is it a yes or a no? Okay, so that is correct. So the total energy is conserved because remember the conservation of energy, that it will not be created nor destroyed but will just be transferred to another form of energy, and that is still the same energy. The total energy will always be the same. That is a yes. So now that we have a small recall of kinetic molecular theory, let's discuss it again. Just a small recap. So the kinetic molecular theory, if you can still remember, we have three scientists that help in formulating this theory to understand how these molecules behave, how this energy affects the behavior of the molecules. And we have Ludwig Boltzmann, the second law of thermodynamics. Later on, we will learn more about him in our next lesson. And we will learn about entropy. So entropy, does it mean chaos? Is it really a chaos? So we will learn it later on. And then we have here Rudolf Clausius. So the kinetic theory of heat, then that will be the relationship of the number of molecules to the kinetic energy, meaning the higher the higher the number of molecules, the higher the kinetic energy is. So for example, in a room of people, the more people inside the room, the more the temperature will increase. So if you if you are only one in the classroom and then all of the sudden your classmates entered the room, all of them are now in the room, you will feel a sudden increase of temperature. It gets hot. So that is the same with this theory of heat. And then we have James Maxwell, and that is, or he is the one who formulated the mathematical formula for kinetic theory. So let's just have a recap about the kinetic molecular theory of gases, as this theory understands the behavior of gas molecules. So how about the solid and the liquid? So later on, let's understand it. So as we know, these gas molecules are in continuous motion and in random motion. However, they do travel in straight line, and only be changed when it collided with the other molecules or the wall of a container. And then also the molecules composing the gas are naturally small compared to the distances between them. So the distances between them are bigger than the size of the gas molecule. Then we have the pressure exerted by a gas in a container will result from the collision. So therefore, if there will be a lot of collision, the higher the temperature we will have. Then there will be no attractive or repulsive forces on this one because these gas molecules are not ionized, so therefore they don't have any charges. And they do not attract or repulse other or atoms or molecules. So how do they attract? So as you remember the plasma is an ionized form of gas. So therefore, what we are seeing now is a plasma. So they do not contain any charges. So when this one had a changes in temperature, pressure, and other external factor, this will change to a gas, and gas is an ionized state. And then therefore, that will be the time it will attract or repulse an atom. Okay. And the next is the average kinetic energy of the gas molecules. As we know, is directly is proportional to the Kelvin temperature. So the higher the temperature, so we will also have a high kinetic energy. So let's have an educated guess in this question. So how will you relate kinetic molecular theory to the behavior of solid and liquid molecules? Summarize the kinetic molecular theory to the behavior of solid and liquid molecules. The solid is rigid or has a rigid structure. However, they don't have any motion. They do move. However, that will not indicate that they are really moving. Just the bond or the forces between the molecules. So that is why they somehow move or like vibrating. Because molecules vibrate, okay? Every molecules vibrate. So that is the beauty of molecules. They are always vibrating. Okay, so molecules are arranged in regular configurations. So they are arranged in 3D, 2D configuration. And they are incompressible because they are already compressed. So therefore, we cannot compress them. And then the density of solid is higher than the liquid. So that is also why you can see the ice floats. Okay, so close together with in the liquid, they are close together with very little space, but they can move. So why they can move and why solid cannot move? So we will learn it later in intermolecular force. And then they are difficult to compress than the gases because of the forces between each molecules, and they are denser under normal condition, and because of this they have different types of attractive forces that we will learn later on. Okay. And also that it can pass one another freely. So Hannah is correct. And it can flow and follow the shape of a container. So why can it follow the shape of a container? Later on, you will learn it. What intermolecular force affects this kind of special property of a liquid. Before we go to intermolecular forces, let's have a recap about electronegativity. So we already learned it in Gen Chem 1 that electronegativity affects the bonding of the atom. So the higher the electronegativity, the more that it will attract the atom. So, for example, we have chlorine, it is negative, and then we have the sodium. So the sodium will be attracted to the negative atom, which is the chlorine. So the higher the electronegativity, the higher the bond that will have, the chance of bonding that they will have. However, we have this Pauling scale that it is a numerical scale that um, measure the bond energy by covalent bond. So, meaning that the Pauling scale is applied to covalent bond but not in ionic bond. So for example here, so as you can see as we go towards here, so our electronegativity increases. And then as we go here from left to right, the electronegativity increases. And our fluorine, oh sorry, and our fluorine will be or has the highest electronegativity. So that is 4.0. So here is the Pauling units. Pauling units. Okay, that is the measurement of the electronegativity in this per element or per atom. So how about, so what is the relation of this to intermolecular force? So let's first discuss ionic character. So ionic character class is how we use the Pauling scale. Okay. So this is to calculate the difference between atoms' electronegativity. Therefore, we can identify if the bond is a non-polar covalent bond, meaning we have equal. So remember the word equal. So we have equal sharing of electrons. And then we have here a polar covalent bond. So we have an equal sharing of electrons. And last is the ionic bond, meaning we are transfer of electrons. So not share but transfer, okay? So for example, how will we know if the covalent bond is a nonpolar and a polar if we don't know the shape, the size of an atom? So we will know in ionic character. So we will use the Pauling scale. If the Pauling scale is less than 0.5, it is a non-polar covalent bond. And if, if the Pauling unit is greater than 0.5, that will be a polar covalent bond. So if it is less than 0.5, that will be a non-polar covalent bond. And if it is greater than 0.5, that will be a polar covalent bond. So let's apply this one. Let's identify if this water molecule, H2O, is a polar or a non-polar. So these are the Pauling units of our oxygen and hydrogen. So we have two hydrogen atoms here. Do we multiply it by 2 to find the ionic character? So we don't need to multiply it by 2, the hydrogen, because we just want to find the attraction between the hydrogen and oxygen, because hydrogen and hydrogen is not affected, diba? Because they have both positive charges, they are repulsing or they are repelling each other. So we have 3.5 ionic character unit. So 3.5 minus 2.1, that will be 1.4. So therefore, what is our bond between this molecule? Is it a polar or a non-polar covalent bond? outer molecule is a polar covalent bond. So that is one way to find out if our molecule is a nonpolar or a polar covalent bond using the ionic character, which we calculate the difference between atoms' electronegativity using the Pauling unit. So this one is a polar covalent bond. Let's proceed. Now we know electronegativity and kinetic molecular theory. So how will you relate it to intermolecular force? So let's have an educated guess. But before we have the educated guess, identify the two terms, the intramolecular force and the intermolecular force. So when we say intramolecular forces, this is between the atoms. So for example, here we have hydrogen and the chlorine, both are non-metals, therefore they are covalent bond. If we have potassium and chlorine, therefore we will have a ionic bonding because we have a metal and a non-metal. Those are the forces between two molecules. So these intramolecular forces are strong forces. So that is why it is hard to break down the compound. So therefore, when you go back to the matter, compound are pure substances because they cannot be broken down. So if you remember the definition of pure substances, that is one of its definition. Next is intermolecular forces, and these are forces that exist between the molecules. So we have also strong and weak intermolecular force. But in this case, we have a weak intermolecular force for this example. Okay? So remember, inter outside, intra within. Intra within, inter out. Winter out. Inter out. Okay, so intermolecular forces. Now that you have the idea what is intermolecular forces, so how will you relate kinetic molecular theory and electronegativity to intermolecular force? So in this case, electronegativity affects the intermolecular forces because electronegativity, when we talked about electronegativity, those are the charges. We have negative and a positive charge. And as we know, a positive and a negative charge attracts with each other. And then if we have likely charge or same charges, it will tend to repel. So later, we will understand what phenomena is this in intermolecular force, and we'll understand the different types of intermolecular force. So how about the kinetic molecular theory? So in this case, when we understand the forces between each molecule, we will understand how molecules behave in solid and liquid. Find it out. First, we understand electronegativity, the charges, the positive and the negative charge. And this is what we call the molecular polarity. So when we say molecular polarity, it is the accumulation of electron density at one end of the molecule. It can either have a partial negative and the other half will have a positive charge. And these are called polar molecules. So when you remember the polar covalent bond or the polar in previous slide, the polar covalent bond has an equal sharing of molecules. So therefore, this molecular polarity will give us how this phenomena develops or will happen. That is what we call polar molecules. And this is what we call a dipole moment. So when we say a dipole moment, this is any system in which there is a separation of charges of charge. So we have a positive and a negative charge. So here, when we say a dipole moment, for example, we have here a hydrogen and a chlorine. So when you look at the periodic table, the hydrogen has or will have a positive charge, okay, slightly positive, and we have here the chlorine will have a slightly negative charge. So this one is a delta. So delta negative. So why is the arrow pointing towards the chlorine? Because remember that electronegativity, by the definition, the electron, the negative, will attract the positive. So therefore, the hydrogen will be attracted to chlorine. So that is why the arrow is pointing towards the chlorine. So therefore, we have a direction. So the movement of hydrogen is towards chlorine. And the magnitude is the distance between the atoms. And if we have other molecules there, so we have a series of connection or hydrogen and chlorine. So therefore, you will see how this dipole moment or other intermolecular forces um, will affect the behavior of this molecule. Okay. However, in a dipole moment, so the bond dipole moments will cancel if they are of the same magnitude. So when we say same magnitude, the distance between the molecule or the distance between the atom is the same. So for example, we have carbon, carbon. So when we say same magnitude, Pauling units are the same. They're almost in the same group or in the same row. So therefore, their Pauling units is less than 0.5. So therefore, they have equal sharing of electron. So therefore, they will not possess this dipole moment. And the next is if they are symmetrically arranged about the central atom. So when we say symmetrically arranged, therefore, they will have an equal sharing of electron. So for example, um, we have here carb, um, carbon, then we have oxygen. So carbon dioxide, and carbon dioxide has this. When you look at the periodic table, the carbon and the oxygen are almost next to each other. They're next to each other. So when you solve this one, you have carbon and oxygen. So their Pauling units will be less than 0.5. So therefore, that is also a non-polar molecule. Therefore, they won't have a dipole moment. And also, they are symmetrically arranged. So let's have an example for that. So that you will see that there are molecules that have a less than 0.5 Pauling units, but in their geometrical figure, they have this symmetrical shape, and therefore they will be called a nonpolar molecule. So for example, we have here a fluorine and boron. Fluorine and boron. Fluorine and boron. So we have 2 and 4. 2 and 4. So when you subtract it to find the units, the ionic character, so 4 minus 2, so we have 2 Pauling units. Okay. So this one, that is correct. So, Mapril, that is correct. So this one is a polar covalent bond because it is greater than 0.5. However, when we look at its geometrical figure or shape, you will see that there will be pooling of electrons. They have the same um, pooling. So meaning at the end, they will have this zero net charge. So when they have this zero net charge, they will have, okay, so the distance The magnitude are the same. The magnitude are the same. So therefore, they are symmetrically arranged at the central atom. So they are equal, equal, equal. So therefore, this bond, this molecule is a non-polar molecule. So therefore, we need to look also the um, geometrical figure of of a molecule. But in our activity, you don't need to look at the geometrical figure. This is just an addition, and maybe you will encounter some molecules. Hey, teacher taught me that this is when you solve this one, you find the ionic character that is a polar covalent bond, and later on you will find out that it's a non-polar covalent bond, because we also need to look at its um, arrangement, geometric figure. Okay? So that is the dipole moment. So any system in which there is a separation of charge, we have unequal sharing of electron. So unequal sharing of electron, the higher the electronegative, the bigger they will have. And then the smaller is the positive charge. However, can we have a dipole moment in ionic charge? Ionic bonding. So as you see or understand that the ionic bond has a positive and a negative charge. However, when you look at how they um, transfer, because ionic bonding is transferring of electron. So the electron is passed to the atom that has a higher electronegative. So therefore, when it gives its electron, both of them stabilizes. Okay, so at this system, there is a none or a non-separation of charges. So dipole moment can only happen in polar covalent bond because we have an equal sharing of a negative and a positive charge. Because in non-polar, remember, non-polar has an equal sharing of electrons. Also, we have diatomic molecules, the oxygen, the, the hydrogen H2O2. Those are non-polar covalent bond. So you will see you don't know which is the positive and which is the negative side. Okay, so that is the dipole moment. And now let's apply the dipole moment to different types of intermolecular forces. And first, before we apply dipole moment, let's first discuss the ion-ion interactions. So from the term ion, when you remember the term ion, you will remember the positive and the negative charges. So therefore, if it is an ion to ion, so it is the attraction between the positive and the negative charges, and it is the strongest type of forces. So for example here, so let's um, wait for it to start all over again. Okay, so as you will see, we have a freely moving electron, and we have a positive and a negative charge, and what you see, they're attracted to each other. So you see that the positive is the one who will go near first to the negative charge, and they will approach and they will stick together. So this is an example of a solid. So that is why you observe a solid rigid structure, and that they don't have any motion between atoms and between the molecules. And that is the kinetic molecular theory of it. It has the potential charge or zero energy. And this, when we say zero energy, so therefore that is conserved. And when it is converted to kinetic energy, that is the same amount of energy that they possess. Okay? And then they will stick together and that will require a lot of energy to be separated. And when they are stick together, they will form an ion pair. And this will tend to grow, cluster, and that gaseous state or gaseous phase will become a liquid or a solid. So you see that this ion-ion interaction is responsible for the development of the solid. So the behavior of the molecule is because of the ion-ion interaction in the solid. So that is why it doesn't have any motion, because the attraction between each molecule is strong. So for example, let's have a concrete example like the salt. So Na and Cl, Na a positive charge and chlorine is a negative charge. So when they bind together, that is ionic bonding. And when there are other molecules, other NaCl, it will form a rigid structure like the table salt. So now we have our solid. So that is an ion-ion interaction. So next, dipole-dipole force. So from the dipole, if you remember the dipole moment, that is a polar molecule, meaning they have a covalent bonding. We are talking about the covalent bonding. So this is an attraction between polar molecules and it is the most or the common interaction in all intermolecular forces, the dipole-dipole forces. So for example, we have here, so an equal sharing of electron and a negative, an equal sharing of electron, and therefore it can attract other molecule or it can repel other molecule. So for example, let's have a concrete example. My favorite, this one is a water molecule. So remember that the oxygen and hydrogen. So hydrogen has this positive charge, slightly positive, and then oxygen will be slightly negative. Oh, sorry. Okay. So you will see that bond that they form. So this red sphere will connect to the hydrogen bond. So, and as you see here, the white or the hydrogen bond repel from each other. So you will see or no connection between the two. So there will be no force. There, no, not no force, but they will repel each other. So that is why the explanation why water can flow freely because of the repulsion of the hydrogen atom and also the oxygen to oxygen atom. But it can attract the oxygen and then hydrogen molecule. So this one is a hydrogen bonding and hydrogen bonding is a dipole-dipole force. Okay, as you can see this straight line, so this one is a hydrogen and it is attracted to this oxygen. So you see this is a positive and this one is a negative charge. So this dipole-dipole force is responsible for the different properties of liquid. Next is an ion dipole force. So it is a combination of what? So a molecule that has ionic bonding and a molecule that has covalent bonding. So that is ion dipole forces. So attraction between an ion and a polar molecule. So for example, we have here same concept. So we use the term attraction and repulsion for this because we have two charges, the positive and the negative charge. So here we have cation. As we know, it always be attracted to um, an ion, and this one, an ion, will be will attract this positive charge. So they will form this ion dipole force. So for example, here, let's have a concrete example so that you can see how this happen in real life. So for example, we have our salt and water. So teacher, how does the salt dissolve in water? This is the explanation. As you can see, and remember that oxygen has a negative charge. And when you see it, the oxygen binds to the positive charge, which is the sodium. And then the hydrogen bond will bond to, okay, because it is positive, the hydrogen bond, it will bind to the negative charge, which is the chlorine. So this is how the table salt dissolve in water. So it is an ion dipole force. So attraction between this ion and molecule, polar molecule. As remember, water is a polar molecule. And next is the London dispersion forces. So meaning we have this, we still have a dipole moment, but it is induced. And it is attraction between a non-polar molecule. So we have this first one is a symmetrical distribution of electron. As we remember, a nonpolar covalent bond has equal distribution or equal sharing of electron. Why do we call it induced? Meaning, it is somehow mimic the behavior of the dipole moment, but it is just a second. So it will not stay, but it will not be what do we call this, um, constant or simultaneously, or it will happen for a long time. So for example, we have here a metal group and the oxygen atom. So as you can see, these are two nonpolar molecules, and this one will be attracted, the oxygen will be attracted to, yan, to the carbon group. So that will be C um, O, okay, or it can be also a hydrogen atom. So let's say it is a hydrogen atom, and this one is a carbon, and this one is an oxygen. But I don't have any concrete example, so that it's just I get this from Google. So let's have this one, a methyl and an oxygen. So it binds in this carbon group, and this hydrogen will bond to this oxygen, forming an alcohol. So as you can see, just a second, okay? It's a momentarily dipole moment. So that is the London dispersion. From the term dispersion, is somehow dispersed, scattered. Okay. The last one is the van der Waals intermolecular force, and we have two types of van der Waals. We have London dispersion force and the dipole-dipole interaction. So van der Waals is the weakest type of intermolecular force, but it is present in all substances, in all attraction of molecules. So van der Waals is always present. Okay, do not forget that. And it will produce a momentary dipole and will result to induced dipole moment. So induced dipole moment is also known as London dispersion forces, depending on the book, but these two are the same. And a nonpolar compound has even charges. As you know, a nonpolar has equal sharing of electron. And the nonpolar compound again will produce a momentary dipole moment, and it will result to the instant positive and instant negative charge. And then it will usually happen between a nonpolar covalent compound. So example like the methyl group and the oxygen group, those are two nonpolar covalent compound. And then they will have this significant interaction between the large hydrocarbon structure. If you can still remember, hydrogen structures are the carbohydrates, the nucleic acid, the fatty acid. So those are hydrocarbon structure. So van der Waals are present in that structure. Okay? So that is the different types of intermolecular forces. So now we know the different types of intermolecular forces. Now we know why we have this type of properties. We have porosity because as you observe, there is somehow a motion, and that will give its way to the other molecule will enter on that very small space. For example, the door, when it rains, it will absorb water. That is porosity. And then therefore, when you open the door, it is hard and it will somehow heavier. And then when the sun shines and this water is evaporates, then you will normally open the door, or you will easily open the door. Now we have ductility to make a wire laster to shine. Magnetic, as we know, so we have a positive and a negative charge in that. So that is why it is magnetic. And same, it can conduct electricity and also thermal. Why? Because it is a good conductor of heat and has high resistance to heat because it needs a higher temperature to break the bond because it has an ion-ion interaction. Ion-ion interaction has the strongest force. Brittleness, elasticity, malleability, and flexibility. And for the liquid, now we understand why it is viscosity because of the dipole-dipole interaction or also hydrogen bonding. And also the fluidity, capillarity, and the surface tension. Now let's go first to the intermolecular forces in liquids. So let's understand it first. So for the surface tension, so surface tension is the measure of the elastic force in the surface of a liquid. So you can see that is why it can form thin sheets because of the elastic force present in that tension, that surface. And it is also the amount of energy required to stretch or increase the surface of a liquid body. Yeah? And if we have a high or a strong intermolecular force, therefore we will have a high surface tension. So that is why some objects can float and some animals can walk on water. So is it possible for people to walk on water? Yes. If we have a very strong intermolecular force and a high surface tension, we can walk on water. And okay, so that is why you can see droplets of water because of the high surface tension. So it creates like a barrier, a thin sheets that will envelope this, for example, here, the liquid, it envelope. So it forms droplets. Next is capillarity or capillary action. So we have here two, the cohesion and the adhesion. So this is why the water follows the shape of container. So this is the tendency of a liquid to rise in a small opening or to pass through small opening. And we have this cohesion. So cohesion is the attraction between each like molecules like the water. So they are attracted to each other. And then next is adhesion, the attraction between unlike molecules. Like here, this arrow, the wall and the water molecule. So that is why it has somehow uh, attractive, like attractive force between the water molecule and the wall of our capillary. So that is why it looks like passing through, diba? Passing through a small fine tube. So viscosity, the resistance to flow, and the greater the viscosity is, the slower the liquid will flow. Therefore, we have a strong intermolecular force with that, and because of strong intermolecular force will have a higher viscosity and than the weak intermolecular forces. So we have a strong intermolecular forces like the dipole-dipole. So the hydrogen bonding has a strong intermolecular force, so therefore it can have a higher viscosity. And also here, um, the OH group, the hydroxyl, the alcohol, and also carbohydrates like the honey. So it can also resist the flow because of strong intermolecular forces in that substance. Vapor pressure. So this is the pressure exerted by the gas equilibrium with a liquid in a closed container at a given temp. And this is called equilibrium vapor pressure or simply vapor pressure of the liquid. So as temperature increases, vapor pressure increases. And with that, we can say that the stronger the intermolecular force of attraction that is present in the substance, then we have a lower vapor pressure. But as you can see here, as temperature increases, the vapor pressure increases. But why it is in this strong intermolecular force, we have a lower vapor pressure. So let's have a concrete example. Water. So water has a boiling point. So therefore, it has a strong intermolecular forces, which is the hydrogen bonding. And this hydrogen bonding needs a higher temperature. So therefore, this hydrogen or the water has a lower vapor pressure first. But as the temperature increases, as the forces between the molecules are broken down, so therefore, the vapor pressure also increases. Okay? So first, at the first scenario, if we have a strong intermolecular force, it will have a low vapor pressure first. But if we apply heat and we increase the heat, so therefore the vapor pressure will increase. So that is why when you put cover on a boiling water, you will see that the top will move. It is because of the vapor pressure. Like the pressure cooker here. Okay. And then next is a boiling point. As we know, it is the temperature required to form or to change the phase of liquid to a gas. And boiling point is the temperature at which the vapor pressure is equal to the external pressure, meaning if we have 1 atm at the external pressure, therefore the inside pressure is also 1 atm, 1 atmosphere. And if the IMF or the intermolecular force are strong, then the boiling point is higher. For example, here, like water, so we have ice, the freezing point is 0. And then this one is the solid and liquid in equilibrium, a freezing point. And then when the temperature increases, so therefore, it will become liquid and we will reach this boiling point. It will vaporize and then liquid and vapor is in equilibrium in this part of temperature until all of those molecules will be converted into a gas molecule. Is water, and water is the universal solvent. It can dissolve any substances, but not the solid objects like your computer, your cell phone. Yes, it can destroy your equipment, your gadget, but it cannot dissolve it. Maybe, but other types of liquid. Okay, so water is a liquid at the standard temperature in 25 degrees Celsius, which is the STP, remember, in Gen Chem 1, standard temperature, pressure, and pressure, so 25 degrees Celsius and 180 atm, atmosphere. So water is tasteless and odorless. If you taste something, that is a mineral or other substances included in the water. And water is transparent and it will be only visible in the electromagnetic spectrum. And water can act as either an acid or a base or a neutral pH charge, which is 7. And some, we can make an acidic water like the lemon juice. So lemon, so that water is acidic. And then we have a base like um, the one that you will bought in water bottles. They're base, okay, water. Then, as we know, it is a dissolved universal solvent. It can dissolve many substances found in nature, like this. Okay. So as you can see, if you still remember the addition and the cohesion, the capillary action, this one is sticking into the wall. So if you observe after um, moving the container, you can still see a droplet of water at the side of container because there is adhesion, attraction between unlike molecule, the wall and the water. So that is why it sticks there. And then later on, the attraction will be because of the gravity present, so it will be pulled towards. So pulling because of gravity, it will go down and will be co cohesion. So there will be cohesion between the like molecules, like the water molecule. And next is a solid um, molecule, other solid IMF. So intermolecular force. So crystalline solids, remember crystalline solid is table salt. You can see it in table salt. They are crystalline solid and they are arranged in fixed geometric patterns or has crystal lattices, meaning they have this intersecting point that they will meet and will create this 3D dimensional figure like sugar, diamond, table salt, and graphite. And we have amorphous solid that they have a random orientation of particles in their solid structure. Therefore, it is somehow irregular shape and they don't have crystal lattices, but still they are solid like glass, plastic, rubber, and coal. So when they are super cooled, they will harden and they will arrange in this what we are using now, like the glass, the plastic, the rubber. So when you melt the rubber, you can see it in liquid state. So let's see this general type. So the arrangement of particles in crystalline solids, as you can see, it is in 3D structured. It is arranged in repeating structure, and we have amorphous solid. We have no particular order, and also we don't have crystal lattice or lattices. And in behavior, when it is heated, crystals can become liquid at a specific temperature. It can dissolve or it can be dissolved. And amorphous solid, it will soften gradually. So if you see videos, TikTok, and you see like, for example, candy, rubber band, so when you heat or the glass, like when you create figurine made of glass, so they melt it with high temperature and then they um, create this figure. So they shape it because it is soft. And then when the temperature, when it cooled, then therefore it will be this amorphous solid. And we have four types of crystals. We have metallic, ionic, molecular, and covalent network. From the name itself, we can identify what type of crystals they are. From the metallic, so these are um, positive ions that can readily lose an electron to form positive ions and would readily gain, but no atoms in the crystal will gain or would readily gain electrons. So it has a high melting point, it is very dense, and a good conductor of heat, and it is malleable. Malleable can form to thin sheets, and luster to reflect or to ability to shine. So some of we are metals now, we have this ability to shine and reflect. So for example, this type of metal. So we have different metals. You can look at our periodic table. And then ionic metals, so therefore are made of ions and has electrostatic interaction and has a very hard structure and high melting point. Therefore, it is a poor electrical conductor, but good electrical or conductor in molten state and also brittle. So for example, here a salt and other, this one is potassium, calcium bicarbonate, the eggshell. Okay, so that is ionic crystal. And we have molecular crystal. So it is an atom or molecules that are held together by these forces, the hydrogen bonding, the dipole-dipole, and the dispersion forces. Why it is not ion and ion dipole? Because we are referring to molecular crystal. We are just in, we want the polar or the covalent bonding. So these are the attractive forces are broken when the crystal melts, soft structure and low melting point, and poor conductor, and also brittle. For example, the flour and the sugar. So remember the London dispersion, it happens in hydrocarbon structure. Okay. So that is why we have sugar and flour here. Both are carbohydrates. Covalent network crystals so are made of atoms in which atom is covalently bonded to its nearest neighbor. So it is usually made of only carbon and silicon, or carbon and silicon, has hard structure, high melting point, and poor electrical or heat factor, and also brittle. So we have here a carbon-rich molecule, which is a substance called diamond, so a mineral diamond. And we have a silicon dioxide, a silicon carbide. So they have these covalent network crystals. So they are amorphous solids, and we have graphite here. Okay. So graphite is a crystalline solid. Okay. So do you have any questions about the different properties of solid and liquid in terms of their IMF, intermolecular force? Do you have any question, clarification? Can you see now the relation between the kinetic molecular theory and the electronegativity to intermolecular force? Or now we know that intermolecular force has or can be applied to the behavior of our molecules through electronegativity. So that is how we relate. So from our educated guess, from our second question, I think that the relation between electronegativity, molecular, kinetic molecular theory, and two intermolecular forces. Last is reading this diagram. So this one is a graphical presentation of a substance in different conditions and pressure, like temperature and pressure. So for example, we have here the different phases, the solid, the liquid, and the gaseous phase. So the pressure here is increasing, and then therefore, uh, we hear compressible liquid, so therefore we'll have a higher pressure. And then here, if you remember the simulation, when you push the gas molecule or the liquid molecule, when you compress it, the cover will blow up. So we have a higher pressure on that. So we have triple point. So when we say triple point, this is where the states of matter, okay, sorry. So the triple states of matter, the gas, liquid, and solid coexist. This diagram is just a presentation. Okay? Different substances have different triple point, critical point, and their temperature and pressure in solid, liquid, and gaseous phase. We have critical point, that is where we cannot distinguish the liquid to the gaseous state. So that is critical point. So we don't know if it is a liquid or is it a gas. So it is hard to distinguish. That is the critical point. So we have the fusion, the melting curve. So this is where the transition between the liquid and the solid state. So freezing from liquid to solid, and fusion, the melting from solid to liquid. So these are this curve will represent your fusion and freezing curve for this one. And also the vaporization or condensation. When we say vaporization from liquid to gas, so liquid to gas in this case we have here, and then we have condensation from gas to liquid. So we will see. Yeah. Last one is sublimation or deposition. The curve on the diagram which represents the transition between the gaseous and the solid state. So deposition is where the gaseous phase will be converted to solid state, and the sublimation from solid state to gaseous state. So that is how you read the phase diagram. So these are the things that you need to see and understand in reading this diagram.